The second problem of IMO 2020 International Mathematical Olympiad, the most prestigious mathematical competition in the world. This is an algebraic problem. We wanna consider the ways again that helps us in algebra and especially in inequality problem. We must use three famous inequalities, and I can say 80% of inequality problems can be solved by these three inequalities. One of them is QM, AM, GM, HM inequality. Another one is weighted AM, GM. And the third one is Cauchy-Schwarz inequality. Here we want to see which of these three main inequalities are useful. Let's see the problem. The real numbers a, b, c, and d are such that these inequality holds and the sum of them is 1. Prove that this term is less than 1. Now, if you consider the three main inequalities that I said already, you can see only one of them has real number, positive real number in the power. It is weighted AMGM inequality. The typical form of this inequality is in this way. We write it. Now, if we replace A with A1 and A1, A sub 1 with A, B sub 1 with A sub 2 with B, and so on, we reach this inequality. Since A plus B plus C plus D equals 1, we can cancel these two terms. And if we write the right hand side first, then we've got this inequality. So we substitute this term that is here by the right hand side, and suffices to prove this inequality, to prove the main inequality. This term here, this inequality, isn't equivalent to the main inequality, but if you prove this inequality, you can prove the main inequality because you substitute this term with a greater term. Now, at first, we prove that the left hand side is less than or equal to 1, and at the end we prove that the equality never holds. So let's prove the inequality, just the inequality at first. Now let's see again, we write this inequality here. And another technique, this technique is not a main idea, but it's an additional idea that you must know. Homogenization. Let's homogenize inequality. What is this? It's that have the same degrees in both sides. The degree of left hand side is 3, and now by using a plus b plus c plus d, we can write 1 as a plus b plus c plus d cubed, since the sum of them is 1, according to the assumption of the problem. Now we write right hand side here first, and we divide the terms into 4 parts. Also by factoring a squared, b squared, c squared, d squared, by the same way we divide the left hand side of this inequality into 4 parts by factoring a squared, b squared, c squared, and d squared. Now we want to prove that each of the four parts is greater than or equal to the corresponding part of right hand side. Let's see what we have here. If you consider the first inequality, you can cancel a squared, and then in the parentheses you can cancel a, after that cancel 2 times b, and it remains b here. 3 times c cancel, and after that by cancelling 3 times d, on the right hand side we've got d. And we know that a, b, c, and d are in the descending order, so we can say that this inequality is true. So the first one is true. By the same way, you can prove all the all other three inequalities, and now we can reach the problem. But there is one thing left to prove. We must prove the equality never holds. We prove it by contradiction. Let's assume, on the contrary, that the equality holds. So these four inequalities change to equality, and we can conclude that b equals d from here, a equals to b and d from here by canceling b and d, a equals c. So we can conclude all of the variables are equal, and by using the fact that sum of the four variables is 1, we can conclude that all of them equals 1/4. And let's substitute 1/4 with to the variables. Then the left hand side will be 5/8, and it is less than 1. So we reach the contradiction. By this contradiction, we proved that the equality never holds. I will upload the rest of the problems in the near future.